So in this paper, the author starts with an approximation of Euler-Heisenberg-Lagrangian, and the approximation being that they will be studying it under the regime that the energy will be less than the mass of electron, and in this case, the Lagrangian becomes this. Mhm. Though this form will be not useful, I mean, it's when we do the variation, it is going to give us the equation of motion. But the main concern won't be my main concern. Won't be studying the equation of motion, because I will talk about it later. But this equation was studied by Adler earlier, and using it, he was able to predict the birefringence of light in a gravitational background with a strong magnetic field. So his calculation showed that if light propagates and we have a vector b, the background magnetic field, and this is the propagation direction of our light, and this is an angle theta. Corresponding to this, there will be the two velocities will be, if the plane defined by these two vectors, one the parallel, there will be two different the velocity of light having a polarization perpendicular to this plane will be something like 1 minus some number, and this will be 8 times that number, and it will be 14 times that number, and this will be when the polarization is in the plane defined by b and k. So here what the author studies is that because of the gravitational background, what will be the change in this propagation of light. So they derived it by two methods. The first one is the simple expansion of the simple variation of action with respect to the potential field. Another is using Dewitt Swinger asymptotic expansion. I won't go into the details of it, but the main point is that we get an equation of form this. There will be three terms here, but the situation we will be studying will have the Ricci tensor set to 0. So in this case, these two will be 0, and this will be, after doing some calculation which I have posted in the description, will be of form in my calculation I'm getting a minus sign in this constant, and this constant is simply I don't remember, alpha square by 90 amp mass of electron. That's it. So now for studying this equation, they used this plane wave. They told that we will be studying using plane wave approximation, and by using this approximation we will be exactly getting the causal structure. I don't know if this statement is correct, and I have formulated this in this my doubt in a question, and this is as well posted in the description. So now the equation, for solving this equation for under the plane wave approximation, so what they do is that this the electromagnetic strength tensor is solved along the lines of the way we solved gravitational gravitational wave tensors, basically this will be a almost a constant. Yeah, for most of the cases uh, this prefactor will be a constant tensor, and all our time dependency will be carried into this phase factor. Now there will be just 3 degree of freedoms in this tensors, and there will be 2 polarization corresponding to E and B, and one will be the magnitude. So for this all 3 cases. First is under the background when we have a gravitational background, weak gravitational background, as in the gravitational wave propagation. So there, this g mu nu can be set to neta mu nu plus h mu nu, and the calculation they did there. Yeah, before that there was another thing. No. So when we substituted this expression in this equation, so because this is constant, and so when we are differentiating, we will be getting 0 1 tensor of this form, d mu theta, and this is represented by k mu for the shorthand notation. And this is the first Maxwell equation, and the second will be the usual, the symmetric equation. This now using these 2 equations and this notation, they were able to reduce the equation in form k square f rho mu minus 2 xi square and this equation is also derivable, and I have posted this in the description as well. So since this tensor, this equation is trivially satisfied by the by an antisymmetric tensor of form, it's already satisfied by this equation. And when we substitute a mu nu of form a mu nu a mu of form something c nu is y theta, this will be of form k mu a nu minus k nu a mu. So this will be thus. So what our goal will be after for the solving of 3 cases, I will talk about it, will be to get this vector and get this vector and the relation between a vector and k vector. So first they solve this case, and when they were solving this case, as this was a gravitational wave, they set this did the calculation is transverse traceless gauge. So basically there will be h will be 0 except for 1 and 2, the indices, and because of transfer they set the h matrix of in form cos omega t minus kz minus b cos omega t minus kz. So for solving this equation, now by noticing it can be seen that this is a homogeneous equation in the tensor f. So once they use a tetrad formulation and a bilinear vector formulation to simplify the expression of this equation, and once they get it, they were able to separate out the 3 independent component of f mu nu. So the equation of form one component, two component, f1, f2, and f3. Now this is a homogeneous equation, and for this to have a solution, a non-trivial solution, otherwise the f1, f2, f3 can be 0, and this satisfies the equation. So for that, we have the usual, that the determinant of this has to be 0, and when you substitute here, you will get that product of this factor, this factor, and this factor determines the, and these are all functions of k, and determines the value of k. Now there are lots of cases which arises when solving this equation, but what happens is that for for a special case, for one root, then there happens that k3, k0 over k3 in the local, in the tetrad formulation, in the local frame, at a point we get the velocity of light to be of form, I don't remember the expression, this, yeah. So yes, b denotes this vector, this expression. So what we found is that this vector, the velocity of light is coming out to be positive for some time, and for some time, and then negative. And so this is the first case when we see that velocity of light is larger than 1. Then in the second case, when they analyze the Schwarzschild metric, they again go in the tetrad formulation, and they put the tetrad, and they use this tetrad, and when they did the calculation, they found that for radial propagation and for radial polarization, and the propagation being in the direction of E phi, we find that kt over k phi to be greater than 1 by this relation, and this constant is defined by the, and for the other case, when the polarization is along this, and the polarization is along this direction, we get a velocity less than 1. So the implication of these two different velocities is that when we do the calculate the deflection of light in Schwarzschild metric, it happens that we are able to calculate this deflection, and we find that this deflection is equal to 10 raised to the power minus 47 into the u, and this calculation is done for our sun and earth system. So this calculation gives that the deflection will be less by into the deflection given by the simple gr, which is around 256 degrees. So this is just very small deflection, and it's just not observable. So they point out about the using this relation, there is a issue of observability. And another thing is that the calculation which they get by here differs from a previous calculation, and they use the explanation that in the gr, and there is another factor of 1 over r cube, and here we have because of gr the potential gets a factor of 1 over r cube in addition to 1 over r. So this causes the discrepancy between their result and the previous result. And lastly, they calculated the change in velocity in Robertson-Walker metric, and there the metric being isotropic and homogeneous, we don't have to find out the particular direction of light propagation, the propagation comes out simply of form 1 plus some constant, and this is large expression which involves r dot and r double dot and the kappa factor as well. But there is an interesting situation when we talk about radiation dominant universe. Then this factor becomes 11 by 4, the coupling constant over t square. Now this t square, around the time of they did the calculation, and around the time 10 to the power minus 23 second, this becomes the perturbation breaks down. This factor becomes almost 1. So they talk about that this relation might have some consequence on a cosmic wave background radiation, and I was not able to find much about it if any work has been done. Now they discussed whether whether this result actually holds some value, and for it they did talk about that the calculation can be proven by the dispersion relation and complex analysis. It can be proven that the calculation we get in here 1 plus something is the lower bound on the change of velocity. So by calculation, that means that there has to be much more change in the velocities, but for the larger wavelength, because here the calculation were done for the order, the wavelength were the wavelength were larger than the Compton wavelength of electron. So there was a lower bound on the on the wavelength, but to analyze higher wavelength we have to to analyze higher energy we have to use lower wavelength, and for that our calculation doesn't hold. Other than that, they gave I don't understand this explanation that because a classical object is constructed in such a way that it's uh, it's a collection of point-like object which satisfies a large scale light cone structure, so we don't have to care much about this change in light of velocity. I don't understand this explanation. And there was one another important thing they talked about, uh, is that there is a similar calculation done using boundary condition, manifold with boundary condition, but there the relation was of dispersive nature, but here it's non-dispersive. I can't prove that it was non-dispersive, but if it's non-dispersive, then the group velocity will be propagating along the calculation along the speed 1 plus something, and this just means that energy was going to propagate at a speed larger than speed of light. And lastly, they talked about that once we were doing this calculation, so what we found that there was a differentiation of the calculation showed that different frames will be the frames were being differentiated for different frames. We were getting different velocity, and this was obviously it goes against the law of the principle of covariance over which GR is built, that all frames are equally valid for calculation. Yeah, that's it.